Okay, let me show you how I'll turn in the homework. So this is helpful on many levels. This is just very convenient. So you have your left, you're going to be clean left edge first of all. So take the fringe off, you're going to clean left edge. Then you take your whole stack like this and just fold it right down the middle, facing you. And once you get that fold in there, then just turn the open side to the right. Okay? The details are important. It's very easy, but you just have to concentrate a little bit. Okay? I'm going to tell the grader that if this isn't done correctly, you're going to lose points. Okay? Because it's really helpful for me if everyone does it the same way. Again, fold it down the middle, turn the open side to the right. Now you're looking at the back of the last page, and that's where your heading's going to go. So I'll draw it up here. What's happening here? Okay, so this is what, in your hands, it looks like this. Right? You're holding it in your hands, it looks like that. Right here is where you're going to put the heading. And put name, 170, 130, the time the class starts, and then the date. Yeah. If you wrote the heading on the inside, no problem at all. Just make sure you do this. Fold it up. So this is the back of the last page, upper right-hand corner. After you fold it and turn the open side to the right. Okay, so. Don't be like this student. First of all, hardly did any work. Left the fringe on. Turn it to the right, and then put the heading on the back this side. So now the heading's here. Okay, this student's going to lose points for not doing it correctly. It's very easy. It takes just a little bit of concentration to follow the instructions. It seems trivial from one student's perspective, but when I have 150 of these, it's extremely helpful to have them all be the same. Okay. Any questions on that? So let's, which way? If you don't have a stapler, this takes care of it. So yeah, staple your homework normally, but if you don't have a staple, the folding takes care of it. It'll all be together. So, and there was one down here, but if you don't have one, it's okay. It'll still get all together. And then just pass them all, stack them exactly the same way, right on top of each other like that. And let's pass to your right. And then on the right side there, you can just put the stack, just put it right on the floor on the brown concrete, right there next to your chair. Okay, while you're doing that, if you haven't taken the pre-test yet, today's your last chance. It's a required element in the course, and depending on your performance, you can earn some bonus on exam 1. So you got to get to PSA 21 before 6:30. You need a Sun card, no calculator, don't prepare for it, but do your best because you're trying to earn some bonus for yourself.
Are those 25 points for the pre-test part of our grade for the class?
All I'm telling you is your performance on the exam gives you some bonus on exam 1.
Okay.
That's it. So don't worry about counting up points per question or anything like that. Just do your best on the whole thing, and then I'll take your score and turn that into a little bit of bonus on exam 1. Other questions? Okay, so I think the flat screen TV problem. What did I do with my pen? Flat screen TV problem and the last one with the graphs. Let's talk about those. I don't know what I did with my pen. So the flat screen TV problem. So it talked about how the ratio needs to be 16 by 9. Is that right? Is all the homework turned in? You can just, all right, here we go. So 16 by 9. I'll try it again here. Okay. So because the TVs are they're specified by diagonal width or by the diagonal measure, let's just go ahead and find that diagonal measure before we even start looking at other size TVs. So if you had a 9 by 16 TV, what would that be? So what would that diagonal measure be? And this is going to help us now to scale it to other TVs. So what principle do we use to find that? Pythagorean theorem would say that we would do the square root of 16 squared plus 9 squared. And it's 18.4. And so then I think, does it ask about a 29-inch TV? So is that referring to which dimension? A 26? 26-inch TV is referring to what dimension? The diagonal. Okay. So the only difference between this now and our other problems is now it's just 3 quantities changing together in proportion rather than 2. So in all the other examples we had, we just had 2 changing quantities that were in proportion to one another, proportional relationship. Now it's just 3. So if I want to get the area of this, area is just width times height, right? So to find the area, I'm going to need the width and the height of this TV. So what can I do? So what looks natural to me is to say, okay, what do I need to do to 18.4 to get 26? What do I need to multiply 18.4 by to get 26? Well, it'd be 26 over 18.4, right? So let's find out what that is. 1.413. What is 1.413 called? No, nothing to do with pi. What is this called? 1.413. Is it a constant multiple? Is that what it is? No, it's not. What is it? It's a scaling factor. It's how much we're scaling up the smaller TV to the larger one via the diagonal, right? So 18.4 scaled up 1.413 gives us a 26-inch diagonal. So now, how do I find the height? I'm going to scale up 9 the same way. So I'm going to take 9 times 1.413. And to get the width, I'm going to take 16 times 1.413. So the new height will be 9 times 1.413. The new height will be 12.717. And the new width will be 22.6. So those are the dimensions of the new TV, because I just scaled up 9 and 16 by the same amount that the diagonal was scaled up. Yes, ma'am?
Why isn't it a constant multiple if you're using the same number to multiply out?
Okay, a scaling factor is what you do to a particular quantity to get a scaled version of that same quantity. Then you have to do it likewise to the others. But it's not constant, because I could also scale this. I could also scale 18.4 by 3. No, so we want a big TV, right? So I could scale it by 10. And when I scaled it by 10, then I'd have 184-inch diagonal TV, 90 high, 160 wide. So the reason it's not a constant is because I can scale a quantity any way I want. Then you have to scale it the same way for the other quantities. Okay? Constant multiple would be what? Constant multiple would be, okay, 18.4. What do I have to do to 18.4 to get 9? So this is the multiplier that multiplied by one quantity gives us a value of another quantity. That's a constant multiple. So we need to multiply by 9 over 18.4. And that would be my constant multiple that would take me from diagonal to height. So the constant multiple that takes me from diagonal to height is 9 divided by 18.4. 0.489. So if I knew the new diagonal was 26, how would I get the new height? Times 26 by 0.489. And that ought to be, that still should be the same. It still should be 12.717.
So then you're constantly getting the same, different heights, but not this, a different TV. Does that make sense? Like you're getting the new measure for the height, but you're not getting the new width and height.
Yeah, you'd have a different constant multiple that would take you from diagonal to width. That'd be a different one, and that's the one that you would get to get the width. Because we got 3 quantities now. So a constant multiple will pair together 2 quantities, because it takes you from one quantity to another. So if there's 3 quantities, we really have different constant multiples that we could use depending on which 2 quantities we're talking about. All right, does it? So those who requested this one, or anybody, have a further question on this one? Okay, the other one was the graphs at the end of the homework. So let's do this one. When I looked at those, the first 2 a little further, the nature of the graph made it kind of hard to answer those questions because it was kind of hard to pick off points. And so the way that we analyzed changes, or the way that we analyzed proportionality of quantities and changes of quantities was using tables, right? So we want to create tables from these graphs. So on the first 2. It was kind of hard to do that, but on this one, it's very doable. So let's start with the quantities themselves. So do we have some x and y ordered pairs here? So when x is 1, y is 6.35. When x is 3, y is 16.05. And when y is 6, 32.1. So we want to check for proportionality. We got 3 different ways to check, right? So a constant ratio would say that y over x would have to remain constant. So when you set up these ratios and check to see if you get the same number, did anyone do this? Do you get the same value? You do not, okay? So y1 over x1 does not equal y2 over x2. Therefore not proportional, and does not equal y3 over. All it takes is one set of ratios to not be equal, and you're done. Okay? So now the second question is, are the changes proportional? Are the changes in the quantities proportional? In order to do that, we want to set up another table that reflects these new quantities of the changes. So how can we get a valid change of x here? So we've got x values of 1, 3, and 6. What's a change in x that we can easily calculate? 3 minus 1. So the change from x equals 1 to x equals 3 is 2. How would we represent that change on the graph? So can you imagine, how can I represent this change of x of 2 on that graph? I would start at x equals what? 1. And what would I do? Move over, straight over, because x goes right to left. Be like this. That would be my delta x equals 2. That should be a horizontal, straight horizontal line. Okay? What's the corresponding change in y to that change in x? It'd be this minus this, and I'm hearing that someone said 9.7. Is that right? Okay? How would that be shown on the graph? It's really important. We do this kind of thing in calculus all the time because it's talking about how the quantities change together. When x increases 2, simultaneously, what does y do? Y increases by 9.7. Or it increases from 6.35 to 16.05, which is a change of 9.7. Okay? We need another change. So let's start with a table. So how can I get another change in x here? Somebody else? What's another valid change in x? From 3 to 6. So what is delta x for that? 3. So as I go from 3 to 6, I'm changing x by 3. How much does y change? 16.05? So now, how do we represent that? Changing from 3 to 6. Starting at 3. See how straight I can make this. Not bad. Okay, delta x of? That's delta x of 3 starting at 3. Corresponding change in y? We can represent this way. $16.05. Let's just stop right there. That's enough to make an initial check. We can make an initial check of proportionality. Take your pick, right? So what do you want to do? You want to do constant multiple, you want to do constant ratio, or scaling factor? So let's do something different now. We did constant ratio here. We said that y over x was different each time, not proportional. So what can we do here? Let's do constant multiple. Constant multiple is the value we'd multiply 2 by to get 9.7. What value is that? The number we'd multiply 2 by to get 9.7 would simply be 9.7 over 2, right? 4.85? 4.85. So if we've got proportionality of changes, then 3 times 4.85 would have to be 16.05, is it? Take 3 times 4.85. So it's not 16.05. So as soon as it's not, as soon as that we don't have a constant multiple, we got 2 different multiples that take us from delta x to delta y, it's over. This is not proportional. So the original quantities are not proportional, and the changes are not proportional.
Does that mean it wouldn't be a straight line if you drew it?
Okay, so he said, now if I were to connect the dots, it would not be a straight line. Is that because of this, the first, or because the changes are not proportional? Because the changes aren't, okay? To have a line, you don't necessarily have to have the original quantities proportional. But if the changes are not proportional, then this is basically, we don't have constant rate of change. That's the big theme that we're going to be dealing with today and next time. Constant rate of change means changes in the quantities are proportional. So if they're not proportional, the changes, then we don't have constant rate of change, and we get something curved. We get something curved in terms of plotting all the points. Any other questions on the homework? Okay, so I have, for that first workbook check that we did last Friday. Okay, should we talk about it? So I'm going to do my explanation all through the graph, and then I'll put some calculations on the top. But so on the x, or the horizontal axis, I'm using the quantity time elapsed since home in hours. So time elapsed since she left home in hours. Remember from our first couple days, is that a changing quantity or a constant quantity? Time elapsed since she left home. Changing, right? It's a changing quantity. Distance from home in miles, changing or constant? Another changing quantity. Okay? So this whole course, the whole course is about learning to analyze and model changing quantities as they change together. All right? So we're analyzing or we're monitoring how the distance changes as the time changes. Okay? That basic idea of how two quantities change together is really the whole course. Okay? We look at different ways that two quantities can change together and how we represent that. We can represent it graphically, represent it symbolically. That's the whole shebang. Okay? So I'm showing that at half an hour, she's 25 miles from home. That's represented by a point. A point shows that at that point in time, she's that far from home. And then at 4 hours in time, she's 245 miles from home. Is that consistent with the setup of the problem? Are we good? Okay. So the question is, so how far did she go? According to the information given, how far did she go? So, did she? Sorry. So from this point that we have here to this point, how far has she traveled? And how do you get that? Subtract 245. Final distance from home minus initial distance from home equals. What kind of quantity is this? Is this a D quantity? What kind of quantity is 220? What symbols could we use for that? So is it a D or a delta D? It's a change in distance. It's a change in distance. It's not a distance from home. This 220 is not talking about 220 miles from her home. It's talking about how many miles she traveled starting at one point to another. So that's a change in distance. What was the corresponding change in time?
3.5 hours.
How do you get 3.5? What kind of quantity is 3.5 hours? A change in time. So, how did they change together? When 3.5 hours went by, distance covered, or the change in distance was 220. And so you had to, it said she traveled at a constant speed, and one of your goals was to find that constant speed. So the constant speed is how many miles she covers in 1 hour. So if we know how many miles she covers in 3.5 hours, what are we going to do to it to get how many miles she covered in 1? We're going to cut up that 220 into how many pieces? 3.5 pieces. If we cut up 220 into 3.5 pieces, each piece will be how far she went in 1 hour. So cutting up, how do we cut up mathematically? Divide. So notice what I just did. So, and that is, what is it, 60, we'll call it 62.9, okay? We'll call it 62.9. That's how many miles she travels every hour. And notice what I did to get that constant speed. I took which quantity? The change in distance over the change in time. Taking the change in distance over the change in time cuts up the distance into amounts of distance that correspond to 1 unit of time. That's what we did. We cut up 220 into chunks of distance that represent 1 hour each. So that gives us how many miles per each hour. And that's the speed. Okay, so that's key right there. So this ratio, if she remains at this constant speed, what happens? This ratio stays constant. Have we heard that before? Okay, we heard this term before, constant ratio. Okay, so keep that in mind. So now, at the 25-mile mark, when she went, if we look at a change in time of 1 hour, what's the corresponding change in distance to a change in time of 1 hour? 62.9. So add together 25 and 62.9. So I just get something roughly correct. Thank you. So for a change of 1, that's delta t. Delta y is, or sorry, delta d, 62.9. Okay. Okay, so should that be 62.9? Should that be added to 25? Why not? That's just the change. The total distance from home, yes, would be added to 25. But I'm just representing the change in distance. Does it make sense? I'm just representing the change in distance corresponding to a change in time of 1 hour. And that's exactly what 62.9 miles per hour means. It means every time she goes an hour, how far does she go? So let's go another hour. Boom. Another 1 hour. How far now? This is what's called constant rate of change. Every time we go an hour, the distance change is constant. It's 62, again, the delta D, 62.9. Okay, what if, starting from the beginning again, so every hour is 62.9, so how much does she go every 2 hours? So what's her change in distance corresponding to a change in time of 2 hours?
123.8.
And where'd you get that?
62.9 times 2.
Right, so what am I doing? I doubled the time. If I double the time, what happens to the distance? What kind of reasoning is that? Double the time, therefore you have to double the distance. Scaling factor. And that looks like this. So this is, call this delta T2 equals 2 hours. So delta D2 would be 2 times double the distance covered in 1 hour. So look, we have a constant ratio. We have scaling factor reasoning. So what about from here to here is what change in time? Here to the end. What change in time is that? So you find that. So what's that change in time and what's the corresponding change in distance? Go. What's the change in time and what's the corresponding change in distance? You find it. What was delta T? 1.5. Okay. Corresponding change in distance? Where does it come from? Yeah. If we go 1.5 times an hour, then we're going to go 1.5 times the distance. Again, scaling factor reasoning. In fact, our change in distance is always what compared to our change in time? So given a change in time, any change in time, how do we get the change in distance? What do we do to it? Tell me. Yeah, it's always going to be however many hours times the 62.9 that we go every hour, to get the resulting change in distance. No matter what the change in time is, 62.9 times the change in time is our change in distance. What's this? No matter what the change in time is, the change in distance is always 62.9 times it. Constant, multiple. So this idea of constant speed or constant rate of change is really all about what? Oh no, don't pack up and start tuning out. This is the big conclusion.
And we have to add 25 to get the right number.
Okay, so he wants to add 25 to get the right number. What do you think? Is it right?
Be like y plus mx plus b.
So we're talking about changes in time and changes in distance. Not total distance from home and time since leaving home. Do you see? Yeah, so if you wanted to... Okay, so this is a totally different beast. D is something with t's in it. Is different than this. Okay? So we got delta D and delta T in a constant ratio. We have delta T is always a constant multiple times delta T. We saw scaling factor reasoning here. So what's this all about? What is proportional here? Is D proportional to T? No. You should have found that by checking some ordered pairs. No, it's not. Is the change in distance proportional to the change in time? Yes.
Only on the highway, though, correct?
That's right. That's right. Okay. So the change in distance is proportional to the change in time. And so this is saying that we have constant rate of change. Or in this case, constant speed. Constant speed means the change in distance is proportional to the change in time. And so all these points that we could find using that reasoning then would end up in what? Looking like what? A line. Okay? Constant rate of change. Changes are proportional. And all the points together form a line. All the points of a given time and a given distance from home will form a linear equation. So if changes are proportional, we have constant rate of change. It graphs as a line. I will post a Friday workbook and reading assignment. See you then.
When it asks you miles, and you want to find 55 miles, how would you go about that?
Let me just turn this off.